So theme of today's session is combinatorics. Today, while talking about combinatorics, there is an important prerequisite. So we will touch base upon that. So it's very simple, but still let me reformulate that for the sake of everyone. Let's say there is a person. This is you, okay? And now there is a box which contains some fruits, another box which contains some flowers. So let's say it contains fruits like apple, banana, and guava. And let's say it contains flowers like rose and lotus. Your task is to pick exactly one fruit and one flower. So you have to pick exactly one fruit and one flower. So it means you could go ahead with any combination. You could pick a guava and along with this lotus. Okay. You could also have gone ahead with apple and rose, right? So the problem is that how many combinations are possible? How many combinations of one fruit and one flower are possible? So the answer is very simple. As a lot of you are saying, six. So you are saying six, and why you are saying six is because your six is coming from the product of three and two, where your three is the number of fruits and 2 is the number of flowers. This is the product rule. This is the basic product rule of combinatorics, right? Where we say that if we are performing any compound action is basically, combination of multiple actions. So if you want to know how many different ways are there to do that, you have to figure out how many different ways are there to perform the first action. The first action is to pick one fruit. Now, because there are three distinct fruits, so if I have to pick one fruit, exactly one fruit out of these three fruits, there are three ways. I could either pick an apple or a banana or a guava. So there are three ways. Similarly, if I have to pick a flower, there are two choices. I can either pick a rose or a lotus. So two choices for this. So 3 into 2 is 6, and that is what the answer is. Now the important thing here is that both of them have to be independent from one another. I mean, if you pick an apple, then you are not being forced to only pick rose or only pick lotus. I mean, irrespective of what fruit you have picked, you always have right to pick two flowers, right? So your choices for this action is not hampered by the choice that you made over here. That is the basic idea behind product rule, right? Now, if everybody is clear with this, right? So now once we are clear with this, what we'll do is we'll pick a question and we will just solve that. Yeah. So look, whether you have understood the question, whether you have read it or not, just look at my screen. I'll make it quite easy for you to understand and then we can process it. Okay. So the question simply says that there are some seeds and plants. Okay. That is what the question is. Now, let's say there is a long lane, something like this, and along this lane, there are some seeds and then there are some plants. So for example, you could have a plant and then a seed and then a plant and then a seed, plant, then again seed, plant, seed, something like this. This is the situation. Now, what the question is saying is we have to put some separators so that each separation has exactly two seats. This is the most important thing. Exactly two seats. Okay. So I want to put some separators so that each separation has exactly two seats. That is the basic requirement over here. So let me just give you a quick example. I can say that, hey, let's do one thing. Let's put our first separator over here. Okay. And then after, let us put our second separator over here. So if I put my first separator over here, then this is my first separation. This is my second separation. And this is my third separation. Can I say that all three of these separations are having exactly two seats inside them? Yes or no? Yeah. You can clearly see, isn't it? Like here, in this separation, there are exactly two seats. In this separation also, there are exactly two seats. And in this separation also, there are exactly two seats. See, the number of plants doesn't matter. Like here you have got three plants. Here you have got four plants, and here you have got zero plants. But for me, number of plants is immaterial. The only thing that I want is that each separation that I have created should have exactly two seats. That's the only important requirement over here. And now there can be multiple ways of doing so. So there may be multiple ways of putting these separators. Like right now, what I just showed to you, I had put one separator over here, another separator over here, right? But I could also have done something like this. I could have just said that instead of going ahead with that, let's put our first separator maybe right here. We can do that. And then let's put our second separator over here. So in that case also, I can clearly say that the first separation has exactly two seats. Second separation also has exactly two seats. And third separation also has exactly two seats. So there can be multiple ways. Now the question is just asking that, hey, how many ways are there? So return me the total number of ways in which you can perform these separations. Okay, so just to take a quick and easy test case, let's say you have a seed, a plant, and then again a seed, and then plant, and then seed, plant. Can you tell me how many ways will be there in this particular case? How many of you agree with three? Okay, so I believe those of you who are saying three are saying so because you are saying that, hey, I can put my first separator here. If I do so, then this will be the first area and this will be the second area, and both of them are having exactly two seats. Okay. Also, you could have put your separator over here. So that also works because this and this also have exactly two seats. And you could also have put your separator over here. So in that case also, this and this have exactly two seats. So there are total three ways. There is no fourth or fifth way. No other ways are possible. Is it absolutely clear to everyone that why 3 was the answer in this particular case? And now one of you very rightly mentioned one important observation. So let me ask that observation to you in form of a question, that if the number of seats is odd, then what will happen? Then no such distribution is possible. So the number of ways will be zero. Just imagine, because you want each of your separation. Let's say this is the first separation, this is the second, this is the third, and that is the fourth. You want every separation to have two seats, two, 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 two. So the count of seat will always be sum of twos, which is an even number. So if the count of seats is odd, you can immediately return that your answer is zero. Is everybody convinced with that? Yeah. Okay. So now when we arrive at the exact question where we have to count the total number of seats, how can we think? How can we start thinking from very basic level? So some of you suggested some ideas, but I would still want to hear again. Generate all the subarrays and then count each of them having exactly two seats. All the subarrays having exactly two seats. See, if you are talking about all the subarrays, there may be issues. Let me illustrate that. So let's say you consider this subarray. This subarray also has two seats. But if you consider this as a chunk, okay, as a separation, then this thing will be left out and this thing will be left out. And now they will be unhappy because they are having exactly one seat inside them. But what we wanted was two seats. So it's not ideal to consider all the subarrays over here. Is that making sense? Okay. Now some of you are saying that from second seat till the next seat, we have some options. That's a very good point. That's an intelligent point. So I would want others also to focus on it. In fact, I am illustrating it. So you can just look at my screen and I'll just resonate with what your friends have said. So you're saying that from second seat till the next one, we have multiple points to put separator. This is what you're saying. Okay, so let me just illustrate. If you just go back to that very simple example that we had taken, I'm just rewriting it. Let's say you have a seat, plant, seat, plant, 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 seat, plant, seat, something like this. So let's say you are maintaining a count of seats. Okay. So initially the count is 0. Now you saw a seat, so the count would become 1. When you see another seat, the count would become 2. Now, from the second seat onwards, the moment you got a second seat, till the next one, what is the next one? The next one is this. So it means that in between this and that, everything is plant, 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 plant. And now what I wanted was that each separation should have exactly 2 seats. The moment I have gathered 2 seats here and here, I can either put my first separator here, or I can put here, or I can put here, or I can put here. Do you agree with this idea? How many of you do? So basically it means the moment you have found second seat, just find out where your next seat is. And in between this and this, you can put your separator at all these different positions. Technically speaking, if this index is, let's say, what is this index? It is 2. And let me write it. This is 2, 3, 4, 5, 6. Then at how many positions could you put your first separator? Tell me. What should be your answer in terms of 6 and 2? It should simply be 6 minus 2. So I can say that if the index of my second seat, if the index of my second seat was index I, and the index of the next seat was index j, then j minus I denotes the number of ways of putting first separator. I'll write it. It denotes the number of ways to put first separator. And now the same logic can be extended. The same logic can be extended on and on and on, and you will have your job comfortably done. Okay, so what I mean by that is, let's say you now have a little longer sequence, and your sequence comprises of seat, plant, plant, seat, plant, plant, seat, seat, plant, plant, seed, plant, seed, plant, something like this. Okay. Can somebody quickly look at this sequence and tell me the answer? Let's see who comes up with the answer fastest. Okay, so let's have a look. Let's have a look. If we just use the idea that we learned over here, what would I say? I would say that, hey, let's start counting the number of seats. Whenever the number of seat becomes 2, we become little careful, because now we know that we have to put a separator, because the moment 2 seats have come, you need to put a separator. You do not intend to have more than 2 seats in any chunk. So you've got your first seat here, you got your second seat here, right? This was your second seat, and after this was your next seat. So you could say that you could have put your first separator either here or here or here. So for putting the first separator, there are 3 ways, right? Now, from here, again, you can reset your counter of seat, because see, if you have put your first separator here or here or here, you have created one chunk. Now, when the next chunk starts, if this is your first seat, your count of seats becomes 1 again, and then 2 over here. And now, in between this and that, there are different breakpoints. So you could say that, hey, now I can either put my next separator here or here or here, right? So how many different ways do you see to put your next separator? 1, 2, and 3. So I can say there are 3 ways of putting my first separator and 3 ways of putting my second separator. And after that, after that, I'm basically done, because this is just the last chunk of 2 seats, and after that there are no further seats. So my total answer will be 3 multiplied by 3, which is equals to 9. Is that making sense? The most important thing over here is this 3 into 3. Why this 3 into 3 has happened, right? Because when you're putting different separators, you just have to figure out in how many different ways you can put your first separator, how many different ways you can put your second separator, how many different ways you can put your third separator, if at all. So if the number of ways of putting your first separator is W1, number of ways of putting second separator is W2, for third it is W3, for let's say the last separator it is WL, then your total answer is nothing but product of all of them. This is the rule of product which we have studied, as the first item in our class, where we said that if there are 3 ways of choosing a fruit and 2 ways of choosing a flower, and if both of them are independent of one another, which means that my choice of fruit doesn't impact the choice of flowers, then I can immediately apply rule of product, and that is what my answer is. Why are we ignoring the last plant? We are not ignoring anything. See, what is our agenda here? Our agenda is to put separators so that each separation has exactly 2 seats. So what are we ignoring? We are not ignoring anything, right? Your last chunk can very well be this. If you just go ahead and put one separator over here, it's totally all right, right? Because this final chunk has 2 seats. That is what we want. We want each chunk to have exactly 2 seats, right? And let's say you had put your first chunk over here. Then you did a perfect job, right? Because this has 2 seats. This also has 2 seats. And that also has 2 seats. So we are not ignoring anything. And I told you already that we do not give a damn about the number of plants. We are just concerned about the number of seats. Why can't we put separator at last? See, there is no use. No, that's what I'm saying. Why do you want to put a separator? Is there something before this? So why do you want to put a separator here? Is there something after it? So why do you want to put a separator? Okay, so this becomes a very simple question now. A simple rule of product has been able to solve this, right? Wherein, and can you code it? How many of you can confidently code it? The only thing to take care of over here would be, okay, will there be case when the number of seats are odd? Yes, definitely. You will have to handle that edge case. You will have to handle that edge case. So if the count of seats is odd, you should return 0. Okay, immediately. All right. Now, if you solve this question, you know that you have to take product of so many integers. And what can happen as a consequence of this? Integer overflow. Okay, so in questions like these, wherever integer overflows can happen, you are usually told to return answer modulus m. Because if answer is infinitely high, you cannot store an infinitely high number inside an integer and long, everything has limits. So in such cases, the question tells to take mod with m. Even here it is asking to take a mod with m. Have you seen that? Right? So if you take mod with m, your result will always be smaller than m, and that way it will fit into an integer and you can return that. Now, while you are taking product of numbers and you want to take a mod, then you have to apply modular arithmetic. So the basic idea of modular arithmetic is that if you want a into b mod m, then this is calculated in this manner. A mod m, for now, just remember this formula, into b mod m whole mod m. You have to take one final mod with m also. That is the idea. Okay, because that is what you're supposed to return, right? I mean, just imagine that you had seed, plant, and then seed, plant, seed, something like this. So you know that for putting first separator, there are 1, 2, 3, 4 choices. And for putting second separator, there are 1, 2, 3 choices. So my answer is going to be 4 into 3. I have to return 4 into 3 mod m. So what I'll have to do is I'll have to do 4 mod m into 3 mod m whole mod m. And if let's say there were more items after that, so let's say the number of ways to put my next separator was 5, then it would be 4 into 3 into 5. So I'll have to do it quite carefully. I'll have to do 4 mod m into 3 mod m whole mod m, right? And now when you are multiplying this thing with 5, again the same thing, into 5 mod m whole mod m. So this can just go on happening in a loop, but you have to make sure that you have to apply this formula if you are trying to return your answer modulus m. So I'll show you the code. Let's take a look at that. Yeah, the mod part will make sense. So let me just write that formula here. See, it's a formula, okay? And we can probably talk someday about it when I teach you modular arithmetic. What is the formula? A into B mod m is A mod m into B mod m whole mod m. This is the formula. Okay. Why we are talking about it? Because the question has asked us that if the answer is very large, which it will be, we have to return answer modulo this value. Okay, which is 10 raised to power 9 plus 7. Okay, now let's look at the core logic. So what is the core logic? See, what I have done here is, just to make things convenient, I am tracking, how many positions are there for the insertion of my current separator. So let's say you have something like this, where you have seed, plant, seed, and then you have a plant, and then you have another seed and dot, dot, dot. So between this seed and that seed, there are 1, 2, 3, and 4 points of insertion. Okay, so I will be storing 4 inside this vector. And now let's say you have a seat, and then again you have PPS. So I can say between this seat and that seat, there are 1, 2, and 3 points of insertion. So I'll push 3 inside this vector, and finally I'll take product of this vector. So are you understanding the intent why I am keeping this vector? It is just to make my job a little easy. I could have done my job even without keeping it. That's a good idea. I mean, that would save your space complexity. But let's take a look. So I have a count, and then I have a total, and then there are some variables like last and first. So what I'm doing is, if the current, the ith character is a seat, I'm doing C++ and I'm doing total plus plus. Total plus plus is to simply count how many seats are there. What is the total count of seats? Okay. So if C becomes 2, let's say at this point of time, C becomes 2, then I will store this index. I will store this index in a variable last. Okay. And when I reach here, the count would have become 3 because it is my third seat. So I can say that now I can assign first to this index. And now we all know that the difference of this index and that index will tell me that how many points of insertion are there for my current separator. So what I have done is that I have pushed first minus last in my vector, and then I have reset my value of count, because now, because the moment I have put a separator somewhere, this is my first seat. So I have reset my count to 1, last and first both to -1 each. So again, this thing will keep on getting repeated. The moment, your count becomes 2, you will set your last to this index. And then the moment you find another seat, you will take the difference of this and that, and you will push that in your vector. So finally, what will happen is when you come out of this loop, you would know that how many different points are there where you could have inserted different separators. And then all you have to do is you have to take product of this vector. Nothing else is needed to be done. Okay. Now, this condition, why I put this condition, you can think about it. Because if total is odd, so if the number of seats is odd, we know the answer is 0. And if the number of seats is 0, then also the answer should be 0. This is another important edge case. Because just imagine, if everything is plant, you can have no separator with 2 seats. You can have no separation with 2 seats, right? So this is also another important edge case. And now this is the mod with which we have to take the modulus of answer. And now in this loop, all that I am doing is I'm doing answer equals to answer into m. But as I told you, I have to use modular arithmetic because I don't have to return the actual answer. If you keep doing this thing, answer will overflow, it will become negative and it will be a crappy garbage value. But because question is asking me to return answer modulo this particular thing, 10 raised to power 9 plus 7, so I'll use modular arithmetic, which will say answer equals to answer. Sorry, this is not into m, this is the ith element, which is pos of I. Yeah. So I'll use modular arithmetic and thereby I'll say answer equals to answer mod m into pos mod m whole mod m. And then finally I'll return answer, job done. So this was the implementation of what we have discussed. Does it make sense? How many of you clearly understand the code? Yeah. Simple enough. What is the time complexity of this? It is just order of n. Exactly, because this loop runs for n times. And this loop also in the worst case will run only for n times, not more than that. Okay. So this was combinatorics in action. Why is the need to decrease last and first by 1? No, we are not decreasing. See, we are just, you're talking about line number 18, right? We are not decreasing. This is not minus equal to. This is equal to minus. Okay. So we are just resetting the value of last and first to some random garbage value. Okay. Yeah. Visual mistake. What would be the space complexity? Yeah, think about it. What would be the space complexity? See, you can completely prevent the space complexity. Instead of storing things over here, I mean, you don't need to store. You can solve this question in order one space also. Just try that out. Okay, good. Now let's get back to our notebook. So the next thing that I wanted to talk about is even more important. So guys, let's say I ask you a question that, hey, you have three fruits, apple, banana, and guava. You have to pick exactly two fruits. How many different ways are there? How many different ways are there to pick exactly two fruits out of apple, banana, guava? So I can see what you're trying to say. You're saying that, hey, I can either pick apple with banana or apple with guava or banana with guava. Is there any other combination? Somebody might say that, hey, let's go ahead and pick guava with apple. I would say it doesn't make sense because it is already picked. You have just reordered. So if you reorder and call that a different combination, it's not right. Okay. So reorderings are not different. Reorderings are basically the same thing. Yeah. So a lot of you, what you have done is you have used a simple formula, and that formula is 3C2, which is NCR. You might have heard of NCR. NCR basically denotes number of ways to pick R items out of N items. Number of ways to pick R items out of N items. And the formula of NCR is N factorial by R factorial multiplied by N minus R factorial. This is the formula. So if you apply this for 3C2, 3 factorial by 2 factorial into 3 minus 2 factorial, you will get 3. Your answer will be 3, right? Now, few very interesting things we will learn from here. So just keep focusing. Tell me, how many of you in your school or college had learned this formula of NCR, but you do not really remember the proof of it? I mean, you do not really remember the logic behind it, that why NCR is expressed in this manner. So I've taken so many interviews in which people had to use this formula, and the moment I change things, they end up getting stuck somewhere. Okay. So the first thing we'll do is we'll understand that, hey, why NCR is equal to this, so that we don't have to remember this formula and all. Okay. And it's very, very easy to understand. It's super easy to understand. You just have to focus on few lines that I'll write, and then it will be perfectly clear. See, have you heard of something called as permutation? Permutation is nothing, but it is different orderings, different orderings of the same thing. For example, if you have, let's say, 1 comma 2 comma 3, it has multiple permutations, right? 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 2, 1, 3, 2, 3, 1. Like, right? There are multiple different permutations. Now, if I ask you that, hey, if there are n distinct elements, then how many permutations will be there? Like in this case, you saw there was 6 permutations if there were 3 distinct elements. So if there are n elements, how many permutations are there? You might have learned it, remembered it, which is n factorial, and that's perfectly true. What is the formula for this n factorial? It comes from rule of product. How? Let us understand. So if there are n items and I have to create a particular ordering. So let's say there are 3 items and I have to create a particular ordering. So in how many different ways I can pick my first item? All the 3 items are currently available. So any of these 3 can fit in here. So there are 3 choices to pick my first item. Once I have picked one of these 3 items, how many items are remaining? 2. So how many ways are there to pick my second item? 2. And once I have picked 2 of these items and put them over here and here, how many items are remaining? Only 1. So how many choices do I have for this final item? Only 1. So 3 choices for this, 2 choices for that, 1 choice for this. So total number of choices 3 into 2 into 1, which is 6. Now you can generalize it. If there are n items and you have to create an ordering, then for the first item, all of these n are available. So there are n choices. Once you have taken one item out, n minus 1 items are available. So for this, there are n minus 1 choices. For this, n minus 2 choices. And for this, only 1 choice. So the rule of product would take their product, and this is product of 1 to n. So we write it as n factorial. So first of all, is this super clear to everyone that why n factorial is the total number of permutations? There are n distinct items. You know what is the most important thing over here? The n items should be distinct. This is a red zone. If they are not distinct, you will be in trouble. I'll show you. Okay. But yeah, okay. So now let's look at the problem where we are saying that, let's say we have some fruits, apple, banana, guava, pineapple, and lychee, something like this. Okay. And what you have to do is you have to pick exactly 3 fruits. You have to pick exactly 3 fruits. All right. Now, let's say you say that, hey, I need 3 fruits. First one, second one, third one, right? If I use the same logic that I ended up using here, what would I say? Right now, all these 5 fruits are available. So how many choices do I have for the first one? 5. That's right. Okay, now one of these is gone, so 4 of them are available. So how many choices do I have for the second one? 4. And now 2 of them are gone, so 3 are available. So how many choices do I have for this one? 3, right? So according to rule of product, what should be the answer? 5 into 4 into 3, which is 60. But in reality, what is your answer? If somebody asks you to pick 3 fruits out of these 5 fruits, you apply this formula, 5C3. And what is the value of 5C3? 5 factorial by 3 factorial, 2 factorial. How much is this thing? This thing is 10. So what is the logical mistake in this? What is the logical mistake in this? Why this thing is 60 and why is my actual answer 10? Yes, because this thing will end up generating permutations of same combo. It will end up generating permutations of same combo. So what I mean by that is, if let's say you ended up taking apple, guava, pineapple, you will also at some point of time end up taking guava, apple, pineapple, and guava, pineapple, apple. In fact, multiple orderings of this would be considered when you go by this logic, 5 into 4 into 3. So now if you look at it carefully, you would say that, hey, think of it in this manner. When we are picking any three items out of these five items, any three, just pick any, maybe let's say A, B, and G. So if you pick A, B, and G, different permutations of ABG would also end up getting considered. Yeah, you can even understand it now. If you did not understand it there, you can understand it now. So when I use this rule of product, what I said, that for first item, there are five choices, for second, four, for third, three. So let's say your first item was A, right? And after that, you picked G and P. But what if your first item was G? Then your next two items could have been A and P. Now you are saying that, hey, this and this are different. I'm saying this and this are not different. This and this are the same because AGP and GAP are the same combination, right? So when you are just doing rule of product, you are getting all the reorderings of the same combination also. But when we are saying NCR or 5C3, we are not interested in the reorderings of same combo. We are just interested in distinct combos. How many distinct combos are there? Is that making sense to everyone? How many of you are able to understand this point? Yeah, so it's a very, very important point to understand, right? Otherwise, people use wrong logic and they are unable to figure out where did they go wrong. Okay, so now what I was telling you was when you used this logic, 5 into 4 into 3, you got an answer of 60. That, hey, I have got 60 different combos, right? But in that case, what really happened? Let's say you got 60 different combos, so many, 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 many. And at some point of time, you also got ABG. Now, ABG, which is apple, banana, and guava. Now, you would also have gotten different reorderings of same ABG, which is you would have gotten AGB, you would have gotten BAG, you would have gotten BGA, you would have gotten GAB, and you would also have gotten GBA. So what it means is that the same thing would be cloned how many times? Tell me, how many times? Six times. And what is this 6? This 6 is nothing but 3 factorial because there are 3 items you picked. Similarly, if you keep hunting in your list of 60 items, you could have picked some other combination, maybe let's say ABL. For that ABL, you would definitely have picked all the other permutations of it. How many permutations? 6 permutations. So what I can say is that every item, every unique item is getting repeated 6 times. Every unique combination is getting repeated 6 times. Why? Because of its permutations. So the moment I divide this 60 by 6, I get correct answer, which is 10. Are you able to connect the dots? So that's the idea. Now you will very clearly understand that what is the formula of NCR. Let me explain it in a very neat and clean manner. So let's say somebody says, hey, I have got n items. First item, second item, third item, fourth item, n minus 1th item, and nth item. There are n items, and I want to know in how many distinct ways I can pick r items out of n items. So you would say that, hey, let me start from the basics. Okay. I want to pick R items. Okay. So this is going to be the first one. This is going to be the second one. And this is going to be the rth one. Initially, all the n items are available. So how many choices do I have for this? N choices. Now one of them is gone. So how many choices for this? N minus 1. How many choices for next one? N minus 2. And how many choices for rth one? It will be n minus r plus 1. Okay, rth one. See, this is r. This is not n. Okay. So for this, n minus r plus 1. Is that making sense? N choices for the first item because initially all the items are available. N minus 1 choices for the second one because you just picked one item. Now you have picked two items for the next one. So for the next one, n minus 2. And for the rth one, n minus r plus 1. Now by rule of product, how many different choices are there? By rule of product, the total number of choices is n into n minus 1 into n minus 2, so on till n minus r plus 1. Now we know one thing very clearly. Every combination would be repeated because of its permutations. What is the size of each combination? R, because there are R items. So how many permutations will be there? How many permutations will be there for R different items? R factorial. So if you divide this by R factorial, that will be your answer. And if you remember, this is nothing. This is exactly what we did here. We said 5 choices for this, 4 for this, 3 for this. So 5 into 4 into 3 divided by 3 factorial. That is exactly what we are doing over here. Now this thing can be written in a different style, which is n factorial by r factorial into n minus r factorial. You can definitely write it like this. Why? Just use your common sense, you will be able to understand. See, n factorial can always be written as 1 into 2 into 3, so on till n minus r, so on till n, right? N factorial, I just have expanded this thing. And this is r factorial, and this is n minus r factorial. What is this thing? Are you able to recognize it? It is nothing but n minus r factorial. So this and this will go away. Now whatever remains over here is just product from n to n minus 1 to n minus 2 all the way till n minus r plus 1, and that is what is written over here. And here you have r factorial. So this thing is nothing but just a clean and clear way to write that. And that is the reason NCR is n factorial by r factorial n minus r factorial. Is it making sense? So you just understood that what is this NCR. Now you do not need to remember it. You can just derive it on your own whenever you want, right? So this is incredibly helpful. This NCR thing is very, very helpful. And this helps us to solve a lot many questions. Okay. So we will just try to see one question, one very interesting question. So we'll take a quick look at that. So I'm just reading along. There are N boys and M girls attending a club to play some game. They need to choose a group containing T actors. T actors are to be chosen, containing no less than 4 boys and no less than 1 girl. So at least 4 boys should be there and at least 1 girl should be there. It is asking how many ways are there to choose a group. Of course, the variants that only differ in the composition of the troop are considered different. So basically, this line is saying that you cannot consider permutations of the same combo. That is what it is saying. And the value of n, m, and t are given to you over here. So there is one important thing. If you take a look here, the value of t is always greater than equal to 5. Why? Because you need to have at least 4 boys and 1 girl. So your team will be of at least size 5. So this is given to you. Okay, no worries. I'll re-explain. So see, there are some boys. So let's say M boys and N girls. Okay. So let's say the number of boys right now is 7 and number of girls is 3. Now just keep looking at the screen. So let's say the boys are B1, B2, B3, B4, B5, B6, B7. They are the different boys. I'm just labeling them with some random names. And the girls are G1, G2, and G3. Now we have to create a team containing T players. Okay, so there should be T players in my team. So let's say the value of T for now is maybe 7. And the rule is that we should have at least 4 boys and at least 1 girl. So it basically means that any team that you create should have at least 4 boys. So let's say 4 seats are fixed for boys and 1 seat is fixed for girl. You cannot have fewer than 4 boys and you cannot have fewer than 1 girl, which is you cannot have 0 girl. Okay, so you can have different combinations of team containing 7 players. Okay, just tell me, can I just go ahead and have a team like boy 1, boy 2, boy 3, boy 4, girl 1, girl 2, girl 3. So tell me, is this a team containing 7 members? Do we have 7 members which we desired for? Yeah. Is it a valid team? Is it a valid team that follows this and this rule? Yeah, it does, right? Because what did we want? We wanted at least 4 boys. And how many boys are there? There are 4 boys. Okay. And at least 1 girl. So we have 3 girls. So yeah, this team is totally valid. But on the other hand, if somebody says that, hey, let me create a team containing B1, B2, B3, so on till B7, is this a valid team? Although it contains 7 members, it is not a valid team. Why? Because of course it contains greater than equal to 4 boys. So boy condition it is obeying, but girl condition is not being obeyed. We wanted to fix one seat for girl. And here we have got 0 girls. So I'll not entertain this team. Okay. So I hope all of you understand the question, right? How many of you are now perfectly clear with the question? Okay. So there can be multiple ways to, solve this problem. So you can see in variety of different ways. You can just in order to take a little larger example, let's say the value of m is 10. So you have got boys B1 to B10 and the number of girls is, let's say, 4. So you have got girls G1 to G4 and you have to create a team of size 7. Okay. So what all possibilities exist? Tell me. What are the different categories? What are the different possibilities that exist? You would say that, hey, the number of boys should be 4 plus something. And the number of girls should be 1 plus something. So one way is that out of these, 7 players, I go ahead with 4 boys. If I go ahead with 4 boys, how many girls do I need? How many girls do I need if 4 boys are there and the team size is 7? I need 3 girls, right? Okay. Another possibility is that instead of picking 4 boys, I pick 5 boys. If I pick 5 boys, how many girls do I need? 2 girls. Okay. The next possibility is I pick 6 boys. If I pick 6 boys, how many girls do I need? 1 girl. The next possibility is to pick 7 boys, but is it even a possibility? Would you want to pick 7 boys and 0 girls? The answer is no. This is not allowed, right? So these are the only 3 categories that are allowed. And all these 3 categories are disjoint. They are distinct. It can never ever happen that a team represented by this was also represented by this. It's impossible because a team in which there are 4 boys and 3 girls cannot be same as a team in which there are 6 boys and 1 girls. So if the count of this combination is X and the count of this combination is Y and the count of this combination is Z, then my answer will simply be equal to X plus Y plus Z. Is that making some sense? Yes or no? Yeah. Okay. Now, can you tell me the count of this combination? You want to pick 4 boys out of how many boys? 10 boys. How many different ways are there to do that? 10C4. So 10C4 is the number of ways to pick 4 boys out of 10 boys. Okay. And how many ways will be there for this? 3 girls. If you want to pick 3 girls out of 4 girls, then how many ways are there? 4C3. So I would say to pick 4 boys, there are these many choices. To pick 3 girls, there are these many choices. And now it's a compound action, this and that. So total number of choices will be this multiplied by that. Similarly, for this category, if I have to pick 5 boys, then I would say total number of ways is 10C5. And if I have to pick two girls, there are 4C2 choices and the rule of product. So this denotes the number of combinations of this second type, which is 5 boy and 2 girl. Similarly, what will be the value of this? Can you quickly tell me? It will be 10C6. 10C6 because you want to pick 6 boys out of 10 boys and you want to pick 1 girl out of 4 girls. The sum of this and that would be your answer. Is that making sense? Okay, so now it looks very easy. You can just use that formula and you can have the problem solved, but the devil still exists. So I'll talk about the main devil. So hang on for some time. That's the main devil. We'll come to it. Just hang on for some time. See, this approach is cool and you can definitely go ahead and solve this problem using this approach, but certain times it's an intelligent idea to use negation. It's an intelligent idea to use negation. So I'll give you an example of negation. What is negation? So let's say you enter inside a classroom. It's a big classroom. And then you want to know that how many students are English speaking and how many of them are Chinese speaking, let's say. So you ask that, hey, those who are English speaking, raise your hands. Now, if so many people have raised their hands, will you count their hands or will you do something else? You will do something else. You will say that, hey, let me not count English hands. Let me just ask how many Chinese are there. So when Chinese folks will raise their hands, let's say there are only 4 of those, you can quickly say that, hey, total number of people is 90 and 4 are Chinese. So 90 minus 4, 86. 86 are English speaking. So if whatever is being negated is small, we should rather compute that. Okay, whatever is being negated. And in this case, let's say if the value of m is 15, the value of n is 12, then here what we were doing was we were listing down the categories which were possible. If you list down the categories which are impossible, then that would be a better idea. Okay, that would be much better idea. So can you just tell me what are the categories that are impossible? So you want to make a team of 7 people, 1, 2, 3, 4, 5, 6, 7, right? So what are the impossible categories out there? So the first impossible category is where you have got lesser than 4 boys. So either you have 3 boys and remaining girls. So how many girls? 4 girls, right? The second impossible category is where you have got 2 boys and 5 girls. 1 boy, 6 girls. 0 boy, 7 girls. So these are the impossible categories because here number of boys is fewer than 4. And now you have to consider one more possible impossibility, and that impossibility is when there are 0 girls and all boys. Now the number of these impossible categories will always be very, very small. Just 1, 2, 3, 4, and 5. And you just have to subtract this from total number of possibilities. So what is total number of possibilities? If there are m boys and n girls, then total number of students is m plus n. And if you want to make a team of T people, then you are basically trying to select T members out of m plus n members. So if you subtract from this that small quantity, whatever you will get would be your answer. Did it make sense? How many of you understood this? So instead of focusing on what are the possible categories, we focused on what are the impossible categories and removed them from our universal set. And that is how we got to our answer. Now, what was this devil thing that I was talking about? Guys, if you compute NCR, let's say you want to compute 30C15, lot of times you will encounter integer overflow. Yes. So if you want to first compute 30 factorial, this itself will integer overflow, right? I think it will. So, but the actual result might fit inside integer. Let's say this value is 989. I don't know what this value is, I'm just assuming. So let's say this fits in an integer, but this numerator doesn't fit in an integer. But if you calculate this integer, you will be gone, you will be done and dusted, right? So what we do is, instead of computing NCR by using this formula, we use something very interesting. And what is that? So some of you are already mentioning some triangle kind of thing, Cartesian triangle and Pascal triangle. So yeah, how many of you have heard about this thing called as Pascal triangle? It's pretty interesting. Just another 5 to 10 minutes and you will get to know what it is. I'll not code it. This will be your homework. You'll have to code it. What is Pascal triangle? Pascal triangle is something like this. If you have seen something like this, 0, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then what do you have? 1, 4, 6, 4, 1. So do you see how the values are generated? Like this 3 is a sum of 1 and 2. This 3 is a sum of 1 and 2. This 2 is a sum of 1 and 1. This 4 is a sum of 1 and 3. This 6 is a sum of 3 and 3. This 4 is a sum of this and that. And do you know what is one very interesting thing over here? The most interesting thing here is that if you look at any row, it is palindrome, like 1, 4, 6, 4, 1, 1, 3, 3, 1, 1, 2, 1, 1, 1, only 0. So every row of Pascal triangle is a palindrome. Now, if you are carefully looking at it, what is this thing? Okay, let's forget about this for a while. This was our 0th row. This was first row. This was second. This was third, and this was fourth row. Is this value equal to 4C0? Is this value equals to 4C1? And is this equals to 4C2? And then 4C3 and then 4C4? Just check that out. You will see yes. This thing is 3C0. This is 3C1. This is 3C2. This is 3C3. This is 2C0, 2C1, 2C2. 1C0, 1C1, and this is 0C0. And now why are they palindrome? Because NCR is equals to NC n minus R. That's common sense. See, 4C0 is equals to 4C4 minus 4. 4C1 is equals to 4C4 minus 1. And this anyway is middle. 4C2 is equals to 4C2. And it's common sense, no? N, you write NCR as n factorial by R factorial, n minus R factorial. How will you write this? You will write it as n factorial by n minus R factorial into n minus r, which again is R factorial. So that being the reason, this thing looks like that. And now you can use a very important property over here, that this value of nth row is being derived from the top two value of n minus 1th row. And technically, if you take a look, what is happening here is NCR is equals to n minus 1 CR plus n minus 1 CR minus 1. See, if this is my nth row and this is the rth value, then what is this? This is my n minus 1th row, and this is my rth value, and this is my r minus 1th value. So I can say NCR is the sum of n minus 1 CR plus n minus 1 CR minus 1. That is exactly what, n minus 1 CR, yeah, sorry, I was right. N minus 1 CR plus n minus 1 CR minus 1. So this is a very important formula that you might have learned in your schools and colleges, but you can see it being reflected here in Pascal triangle. I'm pretty sure you would have generated Pascal triangles in your schools, or not in school, maybe in your first year of college or somewhere. Did you generate it? Yeah, the Pascal triangle. But you see the beauty hidden behind Pascal triangle. It contains NCR values, different NCR values. And now this is pretty interesting. It means that if I just create a Pascal triangle, and I can create every next row from the previous row, right? Then I have got all the NCR values pre-computed without doing these factorial calculations. And that is amazing, because addition will not lead to overflows, but factorial computation most of the time will lead to overflows, right? So you can just compute your you can do Pascal triangle pre-computation, and then you can go ahead and solve that question. So what I'll do is I'll share the link to code of this question, but I want you guys to attempt it first. So what is the first step that you have to do is you have to create a Pascal triangle, and then you just have to use this thing, total minus whatever you are negating. So whatever you are negating, let's say you are negating a value 15C6, let's say, then 15C6 will already be pre-computed. You can build a 2D array. You can build a 2D array Pascal triangle of n cross n, and you can fill all the values inside it. So your Pascal of ij should be equal to ICJ, number of ways of picking j items out of I items. Can you build this Pascal triangle on your own? How many of you can try and build it? Do you know, when I was studying mathematics in class 11th, then our physics teacher, he used to say that mathematics is a language. So if there is any formula which is written, if you try reading it as if it was written in English or French or Hindi or something like that, you would make every ounce of sense out of it. Everything. Even if I don't know about this thing, I can just read it and I can say, ये तो बिल्कुल सही है. I'll say this is perfectly right. How? Let me just prove it. So if somebody writes NCR as n minus 1 CR minus 1 plus n minus 1 CR, I would say why it is correct. Just listen to it. So let's say the value of n is 7. So you have got 1, 2, 3, 4, 5, 6, 7. 7 items. And the value of r is 4. So you want to know in how many ways you can pick 4 items out of 7 items. Now when this thing is being written, and this thing is being written, it represents two distinct categories. Let me first talk about this category. This category. N minus 1 CR. N minus 1 CR means that, hey, we are picking 4 items out of these items only. So we are picking 4 items out of these items only. If you pick 4 items out of these items, will it contain 7? It will definitely not contain 7. I can say for sure that there will be a lot of combinations of 4 items which does not contain 7. For example, 1, 2, 3, 4, 1, 3, 4, 5. So all these categories which are not containing 7 but are of size R will be represented by this. Okay. Now there is another category which definitely contains 7. So there what we are saying is that, hey, out of these n minus 1 items, I will not pick R items. I will pick R minus 1 items only. So I will pick 3 items only. Let's say 1, 3 and 4. And the last item will be 7. Let's say I pick 3 items, 1, 2 and 3. And the last item will be 7. Do you get the point? So this is the category which does not contain 7, and this is the category which contains 7. These are the only two possibilities. So this NCR, which is expressed as this plus that, can be understood in this manner. Did you understand it, by the way? How many of you could relate to the reasoning that I have given, that why this formula makes sense even in this style? Yeah.